Welcome to the lecture on dispersion. In this lecture, we're going to be talking about range, we're going to be talking about variance and standard deviation. In the past week, we talked about how spread out, or sorry, rather, the location of data. We talked about quartiles, we talked about percentiles, and measures of central location. In this particular lesson, we're not going to be talking as much about where data is located, but rather how data is spread out. On a line, on a number line, every single piece of data has a location. But even more than that, when you look at how data is located in relation to other pieces of data and how spread out that data is, that's what dispersion is. A second, there we go. So why study dispersion? Like I said, dispersion is the spread outness or the variation in data. And when we look at dispersion, there are lots of different measures, or really mainly three measures of dispersion. One measure of dispersion is the range, which is the simplest measure of dispersion, and this is essentially the maximum value minus the minimum value in a set of data. The benefits of using something like the range is that it is very simple, very easy to understand. There's only two pieces of data that contribute to it, but also because of that, it's influenced by extreme values. So if you have two extreme values, one high and one low, it might really misrepresent your data. But it is very easy to compute and very easy to understand. Um, a measure that's a little bit more robust, if you will, is the variance. Variance considers every single piece of data in the entire data set. The units are very difficult to work with, though, because you get these units and they really don't make sense. They're not in real world metrics. You see it and you say, okay, this is the variance, but what does that mean? In order to be able to use it, you've got to take the square root of it, which we're going to get to in the next slide. But if you look over at the right hand side, something that you really need to take away from this slide more than anything is the fact that you really need to be paying attention to sample data versus population data. If you're using sample data, if you've got a sample set, you need to be dividing it by n minus 1 as compared to if you have a population, you're going to be dividing for the variance by n. And so that's a really big difference between the two of them. And the reason why is because we don't want to overestimate the variance. And so by dividing it by n minus 1, we're being a little bit more conservative with our estimations. But if you look down below, you're going to see the sample standard deviation. So right there, S stands for standard deviation, and this is standard deviation squared, which we're about to get to standard deviation. Then you've got X, which is the value of each individual observation. X bar, which is the mean, so that's the mean. And then mu is the arithmetic mean, so you've got the arithmetic mean of the population right there, or you've got the sample mean of the population with X bar. And then n is the number of observations, lowercase n is the number of observations in a sample, versus uppercase n is the number of observations in a population. And this sigma right here, this is a lowercase sigma, and that stands for the population standard deviation. So very similar, we've got the standard deviation. So very similar to the variance. The big difference is that this is in real world metric. The only thing that you have to do to the variance is take the square root of it, and when you take the square root of the variance, then you're able to get the standard deviation, which is in the real world metric that you're actually dealing with. And so what is the standard deviation? The standard deviation is literally the average amount that each piece of information or each piece of data differs or varies from the mean. So if you have five different pieces of information, different pieces of data. Each one of those is going to come together to contribute to the mean. So if you have, a 5, a 10, and a 15, you take the average of all of those, and it's going to be 10. And so each one of those contributes to that. But then the question is on average, how much does each one differ from the mean? And the way that you would do that is you would add up, okay, so 5 differs from the mean by 5, 10 differs from the mean by 0, and 15 differs from the mean by 5. You add all of those together, which gives you 10, and then you divide that by 3, which is going to be 3.333. So for that particular data set of 3 points, it's the average is going to be, the average deviation from the mean is going to be 3.3, or 3.3 repeating. So that's all that we're talking about here is, on average, how far away does each data point deviate from the mean? And, you look at that and you're like, oh, but they deviate from the mean by 5. Yes, but you've also got to include the one in the middle already. And so it's like one deviates by 5, another one deviates by 5, and another one deviates by 0. So the average deviation is 3.333. But a standard deviation, so that's the way that you would compute the population standard deviation. But a sample standard deviation considers the fact that, we're only dealing with a sample. We need to really be a little bit more conservative with our estimations, and so we're only dealing with a sample, so we're going to use a slightly different formula. So let me give you another example as to why this is a really good thing that we have a standard deviation. And so I'm going to go to Excel here. And with Excel, I just need to pull this up. There we go. We've got these 2 different Starbucks stores. Starbucks 1 is inside of a shopping mall, and Starbucks 2 is right off of a freeway. And below are the numbers of drinks served per day in the past week at each location. So we're going to calculate the mean, the median, and the mode, as well as the sample standard deviation, because our district manager wants to have a little bit more insight on this. And so we're going to calculate the mean. So I'm going to do equals average. And I'm going to calculate the average right there. And then equals, we're going to calculate the average of the other one too. Oh! The mean for both of these is 500. It doesn't look like they're similar. Let's see, equals mode. And we're going to highlight this. Okay, we've got the mode of 500, and but I mean the mode of this one's got to be different. Oh no, the mode of Starbucks 2 is also 500. Okay, so equals median. Maybe the median is different. So let's highlight this and determine the median. So the median of Starbucks 1 is 500. I wonder what the median of Starbucks 2 is. Also 500. So if you just look at the mean, the mode, and the median, you would actually look at them and say to yourself, okay, these must be the same. They must be very, producing and doing everything very similar to each other. But you look back up there and you're like, they just look so different. There's something off about this. And so we're going to calculate the sample standard deviation, which once again, this is the average amount that these deviate, or are the average spread outness from away from the mean. So equals, let's see, standard deviation dot s. And I am going to teach you guys how to do this by hand as well, but this is just to show you the efficiency of doing it in Excel. And so I'm going to drag this over. There we go. And so, oh, that's a really big difference. And so Starbucks 1, which is inside of a mall, deviates, each observation deviates from the mean on average by $322.74, while each day deviates from the mean by $91.29 at Starbucks 2. And so the district manager wants a little bit more insight into these 2 Starbucks, and what can you tell the district manager in terms of the way that the district manager would understand. So I would say to the district manager, hey, Starbucks 1 doesn't seem to be quite as consistent day over day. There's a lot more variability. Sometimes they're selling a lot more, sometimes they're selling a lot less. While Starbucks 2 is selling very consistently all throughout the week, we need to dive a little deeper. And so you look right up here and you can see, okay, Starbucks 1 is selling really good on Saturday and Sunday on the weekends. But Starbucks 2 is just selling consistently pretty much every single day. And so that's really important to note that, okay, at the mall on the weekends, yeah, they're selling a lot more. That makes a lot of sense. And you might say to yourself, okay, but that does make sense, and I see it, and it's spread out. I see all 7 data points, but you're not always going to see all 7 data points. And so it's really important to note that with larger data sets, being able to calculate the standard deviation is really important. So we've got the standard deviation, which we were just able to demonstrate, the importance of that. There are other uses for or other ways that you can use the standard deviation. For instance, it's not just saying, hey, how spread out is the data, but it's also really important to know, like, for instance, what proportion of the data is going to be within a certain distance from the mean. So there's a theorem called Trebuchet's theorem that basically says for any set of data, for any set of observations, sample or population, the proportion of the values that lie within a certain number of standard deviations is going to be the mean is at least 1 minus 1k to the second, where k is any value greater than 1. So if I want to know, for instance, how many pieces of data fall within like 2.5 standard deviations from the mean, I can use Trebuchet's theorem and say, okay, 1 minus 1 over 2.5 raised to the second, the number of observations. So I worked that all out, and that's going to give me, if you look right down here, I've actually worked that already out. I've got 1 minus 1 over k to the second equals 1 minus 1 over 2.5 squared, which is 1 over 6.25. So 1 minus 1 over 6.25 gives us 84, or 0.84. So 84% of the observations are going to be within 2 standard deviations of the mean, or 2.5 standard deviations of the mean. And that's just universal throughout. 84% of the observations are always going to be within 2.5 standard deviations of the mean, according to Trebuchet's theorem. So let's get an example of that. An average starting salary of lawyers out of law school is $71,299 with a standard deviation of $33,043.43. At least what percent of the lawyers' starting salaries are within 2.5 standard deviations of the mean? So we already determined that it's going to be 84%, but what does that really mean? It's really more helpful not just to say, okay, 2.5 standard deviations of the mean. It'd be much better if I had, I don't know, say some values to go with that. And so looking at some values, let's take a look at how we would calculate that. So I'm going to go back to Excel, and we're going to look at Excel for a minute. And let's see here. So if you come right over here, we've got the standard deviation, which on the previous slide we were able to see that the standard deviation was going to be $33,043.43. So that's the standard deviation, and so we've got the mean is right here. So we've got the mean. Let's put this right here. Control X. So we've got the standard deviation right here. So 2.5 multiplied by SD, or the standard deviation, is $82,608.58. So if you look at the standard deviation multiplied by 2.5, that's $82,608.58. So what Trebuchet's theorem says is that the mean plus or minus this is going to give you 84% of the observations are going to be within the mean plus or minus this value. So if we subtract this value from the mean, it gives us a negative number. So we're just going to say 0. And then if we add this number to the mean, it's going to give us $153,907.06. So according to Trebuchet's theorem, 84% of the population, or 84% of the observations of salaries of lawyers starting salaries are going to be between 0 and $153,907.60. And so that's a very powerful tool to be able to say, hey, I know with these standard deviations, that I can use Chebyshev's theorem to say, this amount of data or these number of observations are going to be within plus or minus this many standard deviations of the mean. But that's with any distribution. And so you can use even more powerful tools if you use a different distribution. For instance, if you use if your data is normally distributed, you can use a different rule. So with the empirical rule assumes that the data is normally distributed. Once again, normally distributed, the shape that is a nice bell-shaped distribution. And when you've got a symmetric bell-shaped distribution, the empirical rule says that 68% of the data is going to be within one standard deviation of the mean, 95% of the data is going to be within two standard deviations of the mean, while 99.7% of the data is going to be within three standard deviations of the mean. Where people get tripped up all the time is don't forget about the extra 0.15 on either side. And so the empirical rule, a normal distribution technically is asymptotic. In other words, it never touches the x-axis. And so you've got each one of these standard deviations away from the mean that 68% is right in there. 95% is within one standard deviation, 99.7% is within three standard deviations, and then off to the side, you still have 0.15 percent is going to be on either tail beyond three standard deviations from the mean. But that's only with pretty much a perfectly normal distribution. And the empirical rule is really beneficial. We have lots of different ways to be able to use the empirical rule and lots of different ways to apply it. And we're going to be applying it throughout the remainder of the semester. This is all that we're going to be doing in this particular lecture. Just basically a general introduction, letting you know that we can use standard deviations, we can use all this different information to be able to gain insight into the population that we're working with. So that's all that we got for this lecture, and I'm looking forward to doing a little bit more math and Excel with you, and also by hand in the next couple lectures.